Hello everyone, welcome back. I wanted to make a video about tension. I know we've dealt with it a little before in some problems, but I wanted to make a video that dealt with some of the specifics. So let's start with something simple. Here are two guys having a tug of war. In between them is a rope which has a tension in it. Now tension itself really is just a force, but it refers to a force that is specifically created by a string or rope. So here I have a rope, these two people are pulling on it. Now the one big thing about tension is that it automatically creates its own third law pair. Let me show you what I'm talking about. So this guy on the left, let's say the rope is pulling him with 30 newtons. If that's true, then the rope is pulling on the other guy too. And there's no way this rope can pull on the guy on the left with 30 newtons and the guy on the right with anything else. So this force also has to be 30 newtons. In other words, if these two guys were on skateboards and they both pulled, they would both come toward each other. Even if one of them pulled, they would both come toward each other because there's no way person A could pull on person B without a third law pair force occurring on person A. This is the exact situation we had when we're talking about Newton's third law, except the forces are in opposite directions. And again, let's say the person B was more massive, then person B would have the lower acceleration. It's the exact same principle. Now, these forces are nice and straight. But what if I rounded this string around a pulley? Well, if this string is pulling this hook with 20 newtons, it is also pulling this hook with 20 newtons. The key point is the tension throughout a string must be uniform. Another question that literally could be asked here is what is the force from the string on this pulley? Well, this part is pulling the pulley this way with 20 newtons. This part is pulling this way with 20 newtons. If I was asked what is the magnitude and direction of the force on this pulley, I would have to create a vector breakup. 20 newtons here, 20 newtons here. This would be the force from the string, force string on pulley. The one thing I do know is this would definitely be a 45-degree angle because these two legs are the exact same values. So where are you going to see problems asking you about tensions? Let me show you. Let's start with the simplest version. So here's a ceiling. I have a string hanging from the ceiling. It is connected to a single object that has a mass. The first thing I'm going to do is make this my target. So I'm going to make a force diagram of this object. First thing I'll do, force Earth on object would be mg. Now, I'm going to say this object is not going anywhere. And the question is going to be, what is tension 1? What is the tension in this string? Well, if this object isn't going anywhere, that means there must be force upward that matches force Earth. And that, of course, is tension 1. Tension 1, therefore, must be equal to mg. If you were asked, how much force is this string pulling on the ceiling with, the answer would also be tension 1, whatever that value would have to be. So if force Earth was 60 newtons, tension 1 would be 60 newtons. And tension 1 would pull on the box and on the ceiling with 60 newtons of force. So this was the most basic situation, but let me show you some of my personal rules of problems like these. I usually think of things in this order. 1, find out how many tensions exist. This is literally how many strings are there. How many strings exist? Because again, if you notice it's the same string, the tension throughout the same string must be uniform. 2, draw a force diagram where the forces converge. This could be on one object or multiple objects, which I will show you. 3, if there's no acceleration, then all forces must cancel. Whatever object you choose, all forces must cancel. That is basically the key to solving these types of problems. So, I have a situation here. Let's say, and now I'm not going to deal with the mass, I'm going to say the weight here, force Earth on object, is 60 newtons. So the question is, what is the tension in each of these ropes? Well, number 1, how many tensions exist? Well, I see a rope here, tension 1, and I'm going to follow this rope. It goes here, it goes over this pulley. This is still tension 1 because it's still the same string, goes around this pulley, This is still tension 1. So if I find one of these, I find all three because this is the same rope. I have the second rope here, which is T2, and I have a third rope here, which is tension 3. Now, a side note, unless stated otherwise, all pulleys and all ropes are considered massless, which means you do not need to worry about how much they weigh. Later on, that's going to change, which is going to make things a little more difficult. But for now, all pulleys and ropes are massless. So part 2 is let's start selecting objects and making force diagrams. The first thing I'm going to start with is this object, the box. If I have 60 newtons down and there's only one force upward from T3, that means T3 has to equal 60 newtons. Now keep in mind, that means T3 is pulling up on the box and it is pulling down on this pulley with 60 newtons. Now I drew these pictures pretty large, so I can do the force diagrams right on them, but doing them on the side is no problem. T3, 60 newtons downward. Now T1 is upward, and there are two of them, T1, T1. We know they are the same value because they are the same rope. That means they each have to be 30 newtons. So T1 is 30 newtons. 30 newtons, 30 newtons. So that means T1 is pulling up here, up here. It is pulling down on this pulley, which I'll call pulley A, make this one B. It is pulling down on pulley A over here. So the question is, what is T2? So if we did a force diagram of A, I would have T1, T1, downward twice, 30 newtons, 30 newtons, 30 newtons. And that means T2 would have to equal 60 newtons. So T2 is 60 newtons. It is pulling up on A with 60 newtons. It is pulling down on the ceiling with 60 newtons. T1 is pulling down on the ceiling with 30 newtons. So another possible question would be, how much force are the ropes pulling down on the ceiling with? The total there would be 90. Another question that could be asked is, how much force is this guy using to hold this rope? Well, the answer is already here. T1 is pulling on his hands with 30 newtons. And if you notice, any object I chose, object A, object B, the box, net force is 0. They all cancel because nothing is moving. But a better way to put it is there's no acceleration here. Okay, let's get a little trickier. So here's my situation. I will again make this force earth on box. I'll make it 60 newtons again. Okay, how many tensions exist? Well, I see a tension here, T1. I'm going to trace it around. This is also tension 1. I'm going to trace it around. This is also tension 1. I see another one here. This is tension 2. And I see another one here. This is tension 3. So the question is, what are the tension of each of these ropes? Give it a shot and start the video again. All right, so let me show you the big pitfall with this problem. The big pitfall is making T1 and T2 both 30 newtons. That cannot be possible. Let me show you why. And I'm going to make this pulley A, this pulley B. I'm going to use pulley A to show you. If I make T2 30 newtons and T1 30 newtons, I have T1 pulling up on the pulley on the left side and pulling up on the pulley on the right side, which means I would have T1, T1. They can't both be 30 newtons, otherwise I would have 60 going up and 30 going down. So that is not possible. However, even if you don't know what the forces are right off the bat, you can still write down a relationship merely saying what has to be true. So in this case, what has to be true? And I'm going to start with the box again. Well, what has to be true is if tension 2 is pulling up on the box and tension 1 is pulling up on the box, then tension 1 plus tension 2 must equal 60 newtons. Just write an equivalency that must be true. The next thing I'm going to look at is pulley A. Looking at pulley A, I have tension 1 up twice and tension 2 down on pulley A, which means 2 tension 1 has to equal tension 2. Now all I have to do is a substitution. I take 2 tension 1, substitute here of the T2, and I get T1 plus 2 tension 1 equals 60 newtons. 3T1 equals 60 newtons. Therefore, T1 equals 20 newtons. So now that I know this, T1 is 20 newtons. That's here, 20 newtons, 20 newtons. It's time to check myself. I can check myself with pulley A. So if T1 is 20 newtons, that means T2 would have to be 40 newtons. I also could have checked it with my mass here. If T1 is 20 newtons, then T2 has to take care of the rest of it, which adds up to 60. Therefore, T2 has to equal 40 newtons. So I just checked this twice, once with the block and once with pulley A. That also means tension 3 must be 40 newtons because tension 1 is pulling down on this side, pulling down on the other side. Therefore, T3 is pulling up on pulley B. So T3 also has to equal 2T1. So now I have all three tensions. All right, let's step up the game a little bit. This is a very common situation to come across. In the middle is a stationary ring. Just as an example, I will again make forced earth on block 60 newtons. Step 1, how many tensions exist? Well, that one's pretty easy here. Tension 1, tension 2, and this is tension 3. There are 3 tensions. So the question is, what are these 3 tensions? Now, once you get pretty solid at this, you can shorthand a few things. So tension 2 is obviously going to be 60 newtons because it is pulling up on the block and it is pulling down on the ring. The ring is not moving. So a force diagram of the ring is going to be really vital because all forces on the ring must cancel. I drew this nice and large to ensure that I can actually draw a force diagram right on this picture. So I'm going to do that. Tension 3 is pulling in this direction. And whenever we have a vector at an angle, we are always breaking it up. So I'm going to break this up to the right and upward. I will merely call this force 3x and force 3y. Tension 1 is pulling the ring directly to the left. It's horizontal. Now looking at this, I have a force downward on the ring from T2. And there's only one component force that is pulling upward. So if there's a force downward of 60 newtons, the upward force has to be 60 newtons. And this makes a right triangle. And if I know any 2 parts of a right triangle, I can get the whole thing. If I want this horizontal force, I can do tangent of the 30 degrees equals 60 newtons opposite side over force 3x. Therefore, force 3x is 60 newtons over tan 30. So force 3x is 103.9 newtons. 103.9 newtons. I can also do this to get T3. Sine 30 degrees is 60 newtons over T3, opposite over hypotenuse. T3, therefore 60 newtons over sine 30 degrees. And something you may have known, if it's 30 degrees, the opposite side is always half the hypotenuse. Therefore, T3 is 120 newtons. So we now have T3, 120 newtons. All right, what is T1? Well, when we're looking at the force diagram for the ring, essentially, we're not even considering T3 because we are dealing with its components only. You are probably going to be asked to solve for T3, which is why I just found it. But considering the force diagram, I am only dealing with its components. I have 60 down, I have 60 up. It is pulling with 103.9 to the right. Therefore, T1 is pulling with 103.9 to the left. And there you have it. The net force on the block is 0. The net force on the ring now is also 0. The x's cancel and the y's cancel. That's basically this in a nutshell. So, 1, how many tensions exist? 2, draw force diagrams where the forces converge. That is typically going to be on an object like a pulley or a ring. 3, If you know the situation does not have an acceleration, or even better, it's confirmed that everything is stationary, like every problem was today, then all forces on any object you choose must cancel. All right, that is my basic lecture on tension. Have a good day. This is Mr. M signing off.